Hello everyone, welcome to the webinar, and if I am audible just give me a thumbs up or type yes in the chat box, and if you can see my screen just give me a thumbs up or type a yes in the chat box. Okay, so we'll be starting with the webinar. So welcome to this webinar on deep dive into DL. I am Aman Ali Siddiqui and I am a member of ISTE-VIT Vellore, a student chapter. This webinar is going to give you a deep insight and an introduction to how neural networks work and function. So let's get started. Okay, so first of all, so what do we have here? The thing we have here right now is the MNIST dataset. This dataset is a collection of 60,000 images of handwritten digits. So you have the digits written as 0 to 9 and like they have the shape of 28 into 28 pixels. Now this dataset is this is also called the hello world of the deep learning community. It is pretty famous and you can just Google up MNIST dataset and you would find this on the net. So by the end of the session we will be building a model to classify the digits on the dataset, and then you'll be able to you will be able to put an image and the model will be able to classify if one of the digits is shown here, right? So let's consider for simplicity the image of a number 4. As you can see, this 4, like it consists of two vertical lines and one horizontal line, and it can be written in various different ways, as you can see. So you cannot actually hard code a machine to detect the number 4 written like this. You cannot actually give the machine an input so that it will give you output as 4. That problem is actually going to be solved by the method of deep learning, and we'll be like diving deep and knowing how to build a model of MNIST classification. Okay, moving forward, what is machine learning? In traditional programming, we give the input and in the traditional programming, we give the input to the program and we get an output, right? But in machine learning, we give the input and the output and we get the program out of it, or we get the algorithm out of it. This is what is machine learning. So this is actually what makes machine learning different from the older versions of coding, and hence we'll be able to like differentiate machine learning from the older versions, right? So yeah, let's moving on to the data science journey. So one fun fact that I like to share is that I see a lot of people over here who are trying to learn data science, but the data science journey is like this. On the first month you will see, the first month you will see a lot of people with you, but as the months go by, the people would slowly and gradually decrease. But trust me, hang out with me on this journey and like you won't regret just hanging out on this journey. It is going to be tough, but at the end the prize that you are gonna get is literally worth it. So just hang on with me, and yeah, it's going to be really amazing. So yeah, and now let's coming on to the neural networks, the buzzword. What is a neural network? It might seem scary at once when you look at it, but trust me, it's very, very, very simple. It is just a combination of 3 layers: the input layer, the hidden layer, and the output layer, and you just have to connect it all. It is literally going to be very simple, as I'm going to explain in the session. You might be scared at this, like scared at looking at this. It is going to be very simple. So just hang out with me and let's see what happens. And basically what a neural network does is it classifies two different categories of data. Like it's just like this kid, it will get some data and it will classify it into one out of the 2 classes, right? So this is what actually a neural network does. Now to get into machine learning, we need to know the concepts of linear regression and logistic regression, which actually serves a base for the deep learning, right? So if you want to understand deep learning in depth, you need to have a solid understanding of linear and logistic regression. That is why we're going to explore more about these topics, right? So yeah, let's get into linear regression. Like let's assume that you are a real estate seller and you have this data. Now this data has the area of the house on the left and the price of the house on the right. Now the area of the house is, let's say, 5 meters square, and the price of the house is 50 lakhs. So for 5 meters square you have the 50 lakh house, and for 50 and similarly for 50 meter square you have a 100 lakh house, right? This is something which this data is collected by a person, and you can analyze this data and you can be able to map this data into a table, right? So let's say if a person comes to you giving you the area of their house and asks you what is the price of their house, so you have to analyze the data that you have and then predict what is actually the price of their house. So what we are going to do here is we are going to plot these points on the graph and then find out a model or maybe a way to get the output, to get the price of the house. So basically what we are going to do is plot these points such that the x-axis is the area of the house and the y-axis is the house price. So this point and this point and this point and this point, all these points are going to be plotted on the graph, and then we are trying to fit a line onto this data. Now we are trying to make a line such that its distance from all these points is the minimum, right? So let's see how that can be done. I could plot a line like this, but I want it to be the least distance from all these points. But this is not what we are looking for, right? This line is actually very far away from those points. So like what would you do? Would you go on plotting for this line, or would you go and plot this line? See, when like you must have been drawing best fit lines in your physics graphs or maybe in your homeworks, right? So what is a best fit line? A best fit line is a line which has the minimum distance from all the points to the line, right? So what we are going to do here is we plan to make a line which has the least distance from all those points. So you can see that these points have a lot of distance compared to this line, where the distance is comparatively very less. Now we are talking about the lines and the distances, so let's give these distances a good name, right? So first of all, linear regression is a method of finding a straight line that best fits a set of points. So by linear regression, we are going to fit a line onto the data set and then like try to find out the best line which could suit this data set. So as I told you earlier, we'll be plotting a line which has the least distance from all these points. Loss is regarded as a penalty for a bad prediction. Now what is loss? Loss is actually something bad. You can just take it says in the name, right? Like loss means something bad, not very good. So we have to minimize the loss at this point of time. We have to try to minimize the loss such that we get a good prediction. The lower your loss, the better your model. So we would try to minimize the loss, and the loss is different in different machine learning models. Here the loss is the distance of this line from this point. So again, the thing which I was talking about earlier, so we have to try to minimize the loss here. We have to try to make this line as distant as possible as close as possible from these points. Now if it is very far away from these points, the loss is very high. As you can see here, this loss will add up and then it will give a huge error. But we don't want that. We want an error to be as small as possible, right? So we'll go for low loss. So as you can see, the distance from each of these points of the line is very less. Like it kind of cancels out. It just centers into the graph, right? So this line is correctly plotted, and this line is not correctly plotted because again it is very far away from those points. So we have to try to make sure that this line is at the minimum distance from all these points, right? Okay, now this is the general equation of line. As you might know, this is the y coordinate, this is the x coordinate, this is the slope, and this is the c value, which is the y-intercept, right? So c is just nothing but this thing, y-intercept. Slope is this. You could also remember it as y2 minus y1. So here the y variable we have as the house price, and the x variable we have as the area. So this is the line that we are trying to plot here. Now in machine learning, we consider that the weight as the slope of the model and the b as the bias. Now what is W and B? W and B is nothing but just a nomenclature for that slope. So again I tell you, it is very very simple. It's just the name of the thing changes from the slope to the weight, and from the c-intercept, that is the c the y-intercept, that is the c value, to B, that is the bias. So this is actually what all is needed for linear regression. And I mean, seriously, you don't need to know a lot about to get started with linear regression. It's just plotting some points and trying to fit a line in such a manner that it is at the least distance from all the points on the graph, lying on the graph. And this is the equation which you can get from the line, right? Okay, so now we get to training a model. We know that we need to fit a line in such a manner that it has the least distance from all the points on the graph. So how do we achieve that? Now there would be two methods to do this. There would be two methods actually. The first method being the gradient descent method, and the second method being the brute force method. Now when you use the brute force method, you just try to fit the line at random places and try to calculate the weights and biases. But actually that is not very efficient because you never know what to do after getting a line. Like in the gradient descent, you try to make the loss less and less and less. You have a direction to go. But in the brute force method, you actually don't have a direction to go. You just randomly place the line in different positions and try to find out what is the appropriate weight and bias for that line. That is basically how to fit this line. Now you yourself could think that this is not very practical, as you might fit the line here or maybe here, but you would never know that if you're plotting the line here, you would never know that you have to go here. You might even go here or maybe go even farther away from the point, right? So we'll be discussing about gradient descent, which could be regarded as the heart of machine learning and also one of the most important methods that machine learning uses, or maybe the whole AI is based upon. Like the main thing that this is actually one of the most important things that I want you to take away from the session. And this, if you understand this, I mean pretty much everything should be clear to you from now on. So that was actually basics of linear regression, and now we'll move on to training model. Okay, so yeah, now coming to gradient descent. Okay, so it is made up of two words, gradient and descent, right? So you might see this graph up here, and on the left hand side we have the loss. The lower the better, as I told you earlier. Loss is something bad which we don't want to have, right? So we have to make it as low as possible, and this is the model parameters. Model parameters is nothing but the value of the area, like the area of the house that we had earlier. It could be anything. It could be the area of the house, it could be the age of the house, it could be any feature that you have in the dataset or that you want to keep in the dataset. Basically it is represented here by theta. Don't get confused, this is the same variable, it's just the names change, so it's the same thing, right? So this is basically the area and this is the loss. So what we are trying to do here, let's say we start at this point. Okay, so we start at this point and now we will try to move down. So gradient and descent. Now we'll try to go down. The descent here means we try to go down the slope. We try to go down slowly and slowly till we reach the bottom. Our aim is to reach the bottom of this graph. You could consider this similar to a bowl where you start on one end and you want to go down to the bottom of the bowl, right? So this is what we're trying to do in gradient descent. We start here with some values of weights and biases. We step once and we reach this point. Now we again update the value of the weights and biases. Now we change the value of the weights and biases, we change the value of the M and the P, and then again we try to find a way to get to this point. Then we again then we again take one step towards the minima. Then again we stand here. Then we again wonder what to do to get to the bottom of the graph. Again we need to get to the bottom of the graph. So we again take one step. Slowly and steadily we come to the bottom of the graph, and at this point and when we reach this point, this is called the minima, and this is the place which we want to reach. This is the place of minimum loss. Okay, so what is the aim of gradient descent? By the gradient descent, we want to go from this point of high loss to the minimum point, which is this thing. So we take small steps and finally update the weights and biases on a linear regression model. So, and then we try to get to the minimum loss. So basically, if I could explain you using this line, so basically we try to put this line in different places. Like let's say we try to put this line here, then we try to put this line here, and then we try to put this line here, and then finally here, and then we get the perfect line. And this line is the line which is the least loss line, like the line with the least loss. So this is the perfect line, and this is the loss which we are looking for, and this is the best line that we can plot. So this will be the best, this will be the line that we need to plot, and this is the correct model for our data. Okay, coming back, approach to find the best parameters. So basically we give the model the input, that is the features, and we give it the output, as I told you in the very beginning of the session. So it takes the features, does a prediction, makes a prediction, and gives it to the computer, and then the label that, see, the thing is we already have our output, so we will compare the prediction and the output and see the difference of those 2 points. Now when we see the difference of those 2 points, we will find that this value is differing from the real value by this much. That is called computing the loss, that we calculate the distance between the real value and the predicted value. This will then update the parameters. Now parameters will be updated, the weights and biases will be updated, and the model will be again updated with the weights and biases, and the line will shift closer towards the points. Then again we keep on cycling this process until we get a good model with the lowest prediction, like with the lowest loss we could imagine. This is how a model keeps on updating, and we get to the lowest loss, right? Okay, now just one more analogy to make you understand gradient descent, because this is one of the most important concept of machine learning. That is why I'm stressing on it so much. So let's say you are on Mount Everest, right? So this is Mount Everest, not Mount Everest, right? So this is the point where the loss is very, very high. Now you want to get to the point where the loss is very, very low. Okay, so what can you do? You have a lot of directions to go, but you will search for that direction, which direction is the most steepest, right? So you will try to figure out the way which to go, so that like you get down the fastest. So you'll search for a steepest slope. Now you go towards this direction because you see that this is the steepest, so you step one here, then loss is reduced. Now you are here, now you are here, so the loss is reduced. Now again you have a lot of options. Which direction to go? Again that depends which direction is the steepest slope. So you go to this point. Now again the loss is reduced. Now what to do? Now again you have an option. Now you can go to the bottom of the mountain, and then you are done. So what we are trying to do is trying to reduce the error one by one to get to the bottom of the mountain, and to minimize the error. That's what we are trying to focus on. Okay, so let's consider linear regression with 2 inputs. You might have understood linear regression, and this is a simple thing. So basically linear regression was one input was W1 into area with one feature, and let's say if you also have the age of the house, so it is just nothing but you just add W2 x2 or maybe add another feature into the model. So you get W1 x1, which is the area of the house and the weight, and you have W2 x2, the age of the house and the weight. Weight is basically how much your model will be dependent on that feature, and you give the price of the house based on these 2 inputs and the bias term. Okay, so this is linear regression with 2 inputs, and I told you gradient descent in 2D. This is just nothing but just consider the mountain example which I just told you. You need to get on one by one to the bottom of the mountain, and that is where the loss is least and the model is the best. Okay, coming on to logistic regression. Now we are over with linear regression finally, and we move on to logistic regression. So again, logistic regression is very simple. You just have to choose between one of the 2 values. Let's consider a very simple example. Prediction of a coin, like it's either heads or it's either tails. So what you do is basically you have a lot of factors on which the coin flip depends, right? You might have seen these tosses and IPL matches where the umpire tosses the coin, like while the player or umpire tosses the coin, and the coin will depend on a lot of factors like the angle of the bend on the coin mass, or maybe in many other factors like the wind direction or the environment factors. So basically, but you get 2 outputs, right? Like either heads or tails. You don't get a third output or maybe something else. So the main idea behind logistic regression is getting one out of the two outputs, and that helps us differentiate linear regression from logistic regression. Logistic regression, you get one out of the two outputs. In linear regression, you try to fit a line, while in logistic regression, you try to categorize the data into two parts. Like you try to put the data into one of the two categories. Okay. Need for an activation function. Okay, in let's say you have a lot of data, you could actually input anything, any data about the wind direction or maybe anything, but here in basic logistic regression, we try to, like I told you, we try to like shorten down the data into 0 and 1 or maybe two categories, right? So this is where the need for an activation function comes. Activation function is nothing but minimizing the huge amount of values into two values, or maybe into a range, into a small range, right? So let's say this is basically nothing but a sigmoid function. Don't be scared by the graph. It is very simple. Again, it is just 1 and 0. If the value on x is greater than this value, then it will go 1, and otherwise it will go 0. So basically it depends on the input which you are giving. You put the values, respective values, family linear model. It will just squish through a sigmoid. It will just make the values, like you put in any value, it will just give you a value between these two. Okay, so this is the range, and this value will be gotten through if you put anything into the function. Coming to the loss function. Now in linear regression, as you saw, we had this thing, the loss function, which we calculated the distance between the points and the line, and that was a loss function. But in logistic regression, what we calculate, we cannot just calculate the distance between 2 points, right? Because again, this is logistic regression, you either have 1 or 0. So basically, if we let's say if you predicted the coin toss as heads and the actual value is also heads, right? So your prediction is true and the loss is 0. That's it. And if you predicted the coin toss as heads and the prediction that came is tails, so the prediction is false. Now that is infinity. The loss is infinity. The loss is very huge. So the loss is either 0 or infinity, and that's it. Basically, you go for the loss function. You can also learn about this equation, but I mean, this is the main basic thing which you need to know for the loss function of logistic regression. Logistic regression in a nutshell, basically what we're trying to do is trying to divide the data into two parts, blue part and the orange part. This is logistic regression. You try to find a line which divides the data into two categories, right? Heads or tails, or maybe 0 or 1. Okay. Now we are done with linear regression and logistic regression. This was very hectic, and now finally we can move on to deep learning. So as I told you, linear regression and logistic regression serve as a base for deep learning. So you need to go through these in order to understand the fundamentals of deep learning and get to deep learning and actually understand what is going on inside deep learning. Now, okay, we had linear regression and we had logistic regression. So basically, why do you want to go with deep learning and why is deep learning better? So in the recent years, we have collected a huge amount of data, and this data is literally a boon for us. As one thing I would like to share with you, neural networks perform much better on like a lot of data, right? And the thing with neural networks is they are able to recognize patterns from data. So a neural network will be able to recognize the data that you give it and able to make predictions on its own. So you don't have to be a domain expert or maybe know a lot about a particular thing to tell about what should be put for the model. You just need to use a neural network and it will figure out what the algorithm is, or maybe it will make structure out of unstructured data, right? Okay, so there's one strange thing with neural networks. Whenever you go with this data, so as I told you, we have a lot of data, we have collected a lot of data in the recent years, right? So due to that, the thing here which we observe is as the amount of data increases, the strange thing happens is the traditional machine learning algorithms start to plateau down. Their performance does not increase. No matter which type of algorithm in machine learning you use, after a certain amount of data, the accuracy or maybe the model quality would not increase. But the thing with neural network is the more data you give it, the better it performs. So the large neural networks with better and more data would be able to perform much better than a small neural network with less data, or maybe a machine learning model. Up to a certain extent they perform like kind of equally, but after a certain extent, if the data is large enough, you can just go for neural network, like close your eyes and go for neural networks. That's it. So this is basically why neural networks are preferred. And this is the neural network structure. As I told you earlier in this beginning of the session, we have an input layer, we have a hidden layer, we have hidden layer 1, hidden layer 2, output layer. So the input layer is consistent of these features x1, x2, x3, different weights, and these weights are connected to these nodes. So basically these circles are called nodes, right? These are called input features. This is called input layer. This whole thing is the input layer. These are different weights. This is a node. This is again a node. This is again a node. So and this is a weight. The weight will determine how much does this feature affect the other node. How much does this affect the other node? Okay. So we'll have a lot of hidden layers inside this. So these nodes will affect this node, or maybe a set of these nodes, and these nodes will affect these nodes, and finally on the basis of all these nodes, all the structure, we'll get an output based on the different weights and the different features that we input into the neural network. So let's consider with our real estate seller example. We have the area here, you have the age of the house here, and you have the bedrooms here, and we have W1, we have W2, and we have W3. So the W1 will determine the weight of this area, like how much preference is to be given to this area. W2 will determine the weight of the age of the house, and W3 will determine the weight of the bedroom. That is how much importance is going to be given to the feature bedroom, like how much the feature bedrooms is necessary for us to calculate the price of the house. So this is the neural network structure. I think it should be clear to you by now that neural network is nothing but just a combination of linear and logistic regression. If you consider using linear regression, I think you would find it comparatively easier because we have weights there. So you could just write down the value of the weights and then compare it with the lines, and then you can just put it in and you will find it easier, kind of. Okay. So here a neural network is drawn in a horizontal format. Now, why is it what do you mean? This is not actually a neural network. This is just a collection of nodes. Like this is one layer, this is the input layer, and this is one neuron which is connected to all the other neurons, right? So let's say the area is 60 meters square, the age is 3, the number of bedrooms is 4, and the bathroom is 2. So this neuron will be connected to all these neurons. So this will serve as the first layer or the input layer of our neural network, and depending on these values, it will glow or not glow, or maybe it will activate or not. Like we talked about the activation function earlier, so that feature would be implemented here. Now let's I talked about unstructured data, right? So let's consider an example, like when we are going to sell houses. So there's one strange fact, if you notice, like when the age of the house is less, like if there's a new house, right? So the price of the house will be very high when it is very new, like the age of the house is very less. And let's say as it gets older and older, let's say 10 years, 20 years, 30 years, then the price slowly starts to go down. Then after a certain point, let's say the house becomes of 100 years old. Now what is strange about this fact? Now if you observe that this house will attain historical importance. Now if you just put in a machine learning model, or maybe you do proper calculation, you cannot just figure out why is this happening, because it is known by human or by human intuition that after 100 years a thing will attain historical importance. So this is an unknown feature, and this is something which you don't know. So you actually want to know this pattern, and a neural network has this capability of finding these patterns out for you. So basically a neural network can detect that after 100 years this house will actually be more worth compared to the time span between 0 to 100 years. So after 100 years this house becomes of antique importance, and after 100 years this house has a higher price. So this is a pattern, like you start with higher value, then you decrease it till 100, and after 100 it again starts increasing. So these kind of patterns are like recognized by neural networks, and then you can like update the weights and biases and do back propagation or update the model to get better output. Okay, so here we have all the nodes. So one funny thing which you would observe here, that this node is connected to all the 4 nodes, while this node is connected to only 2 nodes. Why is it so? Actually what we are trying to represent here, this node is also connected to all the nodes, but this node is more dependent on bedrooms and bathrooms. So this node will be more closely attached to these 2 features instead of being attached to these 2 features. So this node will compare bedrooms and bathrooms, and while this node will focus more on area and age, bedrooms and bathrooms. This will focus on every feature, and these 2 nodes will finally give us what will be the price of the house. One more fun fact which I like to point out: consider a house having 6 bedrooms and 1 bathrooms. Now this is again something you would not expect a machine to know. Don't you feel that if a house has 6 bedrooms, like it is made for 6 people and it has 1 bathroom, it is very strange, right? Because usually what you would want is 6 bedrooms with 6 bathrooms. So the issue here will be the bed, like as the number of bathrooms per bedrooms decreases, like if we have less bathrooms per bedrooms, then the house price will go down. So this is again a strange pattern which only a neural network or a human like me or you could observe, but a machine cannot observe. So this is where the application of neural networks comes in. And again you can see that this neuron is attached to all 4. This is attached to area. It says area matters. This neuron says I look for bathrooms per bedrooms. Okay, so this is actually looking only for this feature, and this and the best fact is we don't need to tell it to look for this feature. It automatically is able to recognize that this feature exists in this dataset. So sometimes even neural networks perform better than humans on recognizing patterns, and that is a true fact. So here is a representation of the neural network model on a larger scale, where you have the input layer, this is the hidden layer, and this is the output layer. So basically area goes into these nodes. Some of the nodes are activated because they are affected more and the area is good, so this node is activated, and this node will give the output to this node. And similarly all nodes combine to give a final value. This is our final output layer, and we get the value. Okay, so you now know about linear regression, you now know about logistic regression, you now know about neural networks, the basic structure and how they function. They are divided into 3 parts: input, hidden, and the output. Linear and logistic regression I told you about earlier. Okay, I hope you understood it properly. Now coming on to the main thing that we are going to focus on this webinar is handwritten digit classification. So as I told you in the very beginning of this webinar, we had a collection of digits, right? And those digits were handwritten, and it was a 60,000 image dataset collection called the MNIST dataset. So what we'll be doing here is we'll be classifying those digits, those handwritten pictures, so that we can get a number based on those pictures, right? We'll be classifying those pictures, so that our model is able to recognize that what is written, and then it will to tell us what digit is written on it, right? Okay, so let's consider the image of a number 9. So first of all, what do you mean by image, and how is it represented on a computer? Okay, so this is one of the images which I got from the MNIST dataset. It is image of a number 9. Of course it is written by hand, as you can see. So in computers, the images exist in the form of pixels, right? So what are pixels? Pixels are basically a collection of the, like, you have the image, so it is composed of pixels, and each of these pixels have a value that denotes the color of the image that we have, right? So here generally what do we have in images? We have 3 channels, red, green and blue in the computer, but here we will be working on the MNIST dataset. So in this we have image of the 28 and 28 size. The 28 and 28 size that I am speaking about constantly is nothing but the number of pixels of the image that we have here, right? So here if you can see, we have 28 and we have 28. So this is again nothing but the number of pixels we are having inside the image. So again, when we are going to train the model, you will be seeing that these values exist between the range 0 to 255. Again, that 0 to 255 defines the range in which the values of the image exist, right? So 0, like and then what we're going to do is divide that 0 to 255 by 255 so that we get a normalized range. Now the thing which we need to focus on here is that the range which we are having will be between 0 to 1, right? And the value of each of these pixels will be dependent on the value of the number that the pixel stores. So let's say let's consider one of the pixels, right? So I think if you will not be able to see here, so basically this pixel has the value of 0 and this pixel has the value of 1. So what I'm trying to say here is we have 28 and 28 pixels, that is basically 784. You will know why I'm writing 784 here, because I'll explain it later. So again, then the value of each of the pixels is going to lie between 0 to 1. It's going to start from 0 and end in 1. The middle values, let's say the 0.58 is going to be gray in color, and the color of these values is going to increase from 0 to 1, right? So the basic point which I'm trying to point out here is you start with the value 0, that is black. You move on slowly and slowly and slowly, it gets brighter and brighter and brighter and brighter. You reach 0.5, it gets grayish. You reach 1, it gets white in color. So basically an image is a collection of the number of pixels such that it represents a number 9. And then this is 28 and 28 size, so we will try to make the image, the pixels into 784. So in our model we will be taking the input in a one-dimensional format. So this is the reason why I have written 784 here. I'll explain why do we need 784 inside our model, and why cannot we just input a whole 28 and 28 matrix inside a model, and that would actually cause errors, right? So I'll explain that why they're converting it into a one-dimensional numpy array and then proceeding, right? Again, this is the image that we are going to process. Okay, so this is actually where the whole neural network comes together. And so you have an image 7, right? We are talking about linear regression, we are talking about logistic regression, we are talking about neural networks, we are talking about machine learning. Okay, so we take this image, we have it on an MNIST dataset, the number 7. It is of the dimensions 28 into 28. Then we again I told you, okay, how much the value of each of the pixel, how much the value of each pixel is. It lies between 0 to 1, that is, and the values are stored in grid format. Then you convert these values into an array and place it here, the input layer, right? So this is the whole theory of the model which I'm going to explain to you, and then we'll work on the code. So I mean, it will be better for you to understand what actually is going on here before diving into the code. So just give me a minute and I'll explain you the whole thing, how exactly we are integrating everything here, and then I'll explain it in the model. So the pixels are converted into a 1D array, and this 1D array is 784 pixels of different values, and depending on the number of ones and zeros, basically how much each value is glowing, and the value each pixel is storing. Let's say 1 pixel is 0.5, 1 pixel is 1 pixel is 0. So depending on those combinations and those features, so here we have 784 features, right? Like the area of the house, the weight of the house, the age of the house, everything. Consider that to be 784 here. 784 nodes going on to this layer. Now this layer, in this layer, what is happening is each of the node is connected to each of the other node. I mean, it would not be very clear to you in this picture, but consider that each of the node in this layer is connected to each of the node in the other layer. And one more thing, each, like this is 784, right? So this is less than 784. The number of nodes here will be less than 784. And then let's say here some nodes are glowing, right? So you can see that. Why is this so? This is so because some nodes will have the combination needed to glow based on the input nodes. Let's say we are taking 7. So 7 gives you a combination of the input layer such that you get the second layer glown in a proper format. And again, this thing is repeated into a second hidden layer, and again this thing is repeated into a third hidden layer. So the output layer. Output layer has the value of 0 to 9, and the lines which we have here is nothing but the lines which we are having here is nothing actually but the weights which we talked about earlier and the biases. So what we are trying to do is trying to modify this neural network, try to picture this neural network as a linear regression model, or maybe consider this to like take a value, make it activate another node. What do you mean by activation? I told you about sigmoid, right? You take a large range of values and then you give a value of yes or no. So basically in logistic regression you classify it into two categories, right? So basically as I also told you that in the very beginning, I told you neural network is classifying it into two categories. So it will either blink or not blink, you could consider it like that. And again, depending on this, it will blink or not blink on this depending on the earlier node. Finally, it all culminates into the last layer, where if let's say you have the number 7, then this node will blink. If we had the number 9, then this node would have blinked, and similarly the respective node would have blinked. Now what we'll be going to do is we'll be trying to code this into a machine learning model. I'll be showing you the Python code to do this practically, and like I think you might have now understood it. I tried my best to explain it to you in the picture itself. So now you will be able to get into what actually is happening in the code. Okay, so let me just change my screen to the code collaboratory, Google Collaboratory. And Google Collaboratory actually is a Google Collaboratory is kind of an IDE provided by Google, but the thing with Google Collaboratory is that you have the power to access the resources on the cloud, right? You can access GPUs, graphical processing units, and TPUs, tensor processing units, that are specially made by Google. Like TPUs are a feature made by Google, right? So you can use those processors and then use this for your use those processors for your calculations. Now this is very beneficial for machine learning developers, because the resources in machine learning community are very limited. Like you can use your own machine for computing calculation, but it would be much efficient and faster if you go with Google Colab. So you just need to log in and you can just access Google Colab, right? So now let's get into how we are going to create the model. So, and one more thing, the Google Colab consists of cells instead of a IDE, regular IDE. In a regular IDE, you write the code and then you run. instead on Google Colab or maybe any other Python based or maybe data science based IDE, you have cells. So cells is basically you run sections of code to actually visualize what is happening inside the code, right? So do use Google Colab, and regarding the code, you could get the code inside the description, which in the video, which like the description of the YouTube video, the GitHub repository link will be mentioned. You could access this code from there, and then you could follow along with me, and like you would code along with me if you want to. You just need to run the cells to get the output, and I'll explain what the outputs like what the code is doing actually, right? So you could just go there and like go just look for this file, deep dive into dl.ipynb, and you will get this link. Just click on open in Colab, maybe that option or that button would be there. Just click on that, it will open you to a collaborative notebook, and then you can just look at the same screen which I am looking at, and then you get started. Okay, so first of all we'll be starting by importing the necessary libraries here. So pandas is a library in Python which is used for storing the data in a structured format. As I showed you, we had the data stored in a data frame in the very beginning. When I asked you to consider yourself as a real estate seller, you had a data frame, right? So that is something which pandas will help you to do. It will create a data frame or a table for you to store your data in a structured format. So we import pandas as PD. PD is a alias for pandas. You can just write PD whenever you want to use pandas. Similarly, this is going to be for all the libraries. Matplotlib.pyplot is a library for plotting the images. Right now we are not going to make any plots, but we are going to show the images, so that's why we need matplotlib.pyplot. So we just need to import it to show us the images which are there in the MNIST dataset. Then NumPy is used for mathematical calculations. NumPy has a lot of features. You can definitely go and look up the documentation of these libraries. Trust me, it is very good and cleanly written. So NumPy is basically used for mathematical calculations, and then you can just import it. TensorFlow is an end-to-end machine learning and deep learning library. You can import TensorFlow as TF, and basically it will you just have to write one line of code or maybe 2 or 3 lines of code, and the whole neural networks and everything that I just explained to you, that TensorFlow handles it. Okay, so loading the dataset from the built-in datasets of TensorFlow. This is the MNIST variable, and in this we are calling tf.keras.dataset.mnist. Okay, let me run. Okay, so yeah, let's run this, and you want to these libraries are imported. We get to the keras.dataset.mnist. Xtrain and y, you just this function, what this line will do, this line will load the dataset and divide it into xtrain and ytrain, xtest and ytest. Xtrain and ytrain is this, the xtrain is the value that you are giving, and ytrain is the value that you are testing against it, right? So you give the value x and you test it against value y. Similarly, you give that value the value of x test, and you give and test it against value y. So x is the input you are giving, and y is the output you are getting. Train test bit does one thing. We'll be training the model, or we'll be fitting the line on this data, while we will be testing the model on this data. What we are trying to do here is we are trying to show the model this data, and then it will finally predict that this what is actually the output, right? So we just do xtrain.shape. This will give us the shape of the data. Shape of the data is 60,000 images. Xtrain is a collection of 60,000 images or 28 and 28 shape. So basically this is as I told you, MNIST is a collection of 60,000 images. So this shows us that, and then you have plt.imshow. plt.imshow xtrain 111. So this is the 111th indexed picture of the xtrain dataset, and then you have this, and then you have plt.imshow. So basically you plot this image here. Then you have xtrain1.shape. So what this is doing is that this will show you the shape of the xtrain. This will show you the shape of this image. Now xtrain1, okay, when we write xtrain1, what will this show? This will show a NumPy array, 2D NumPy array. As I showed you earlier, we had a 2D NumPy array which had two dimensions, right? 28 and 28. So basically what we're looking at here is nothing but a 2D NumPy array which will have the values between 0 to 255, as I again told you earlier, 0 to 255 because the value of the pixels are stored between 0 and 255. So here we store the value of NumPy arrays like this, right? And okay, you might see these two brackets here, right? This indicates that one array ends here, one array ends here, and these are all two-dimensional arrays. This is 28 into 28. And okay, now what we're going to do is we're going to normalize these values into 0 to 1. We are trying to go and make these values fit between 0 to 1, as I showed you in the slides earlier, right? We want to fit these values between 0 to 1. If it is 0.5, then it is grayish in color. If it is 1, then it is bright in color. Similarly, that is similarly what we are trying to do here is we are trying to divide by 255. When we divide by 255, the value will lie between 0 and 1. Okay, so you could just run it like this, or maybe you could run each of the modules one by one, or maybe run it like this. This way it will just run once and it will be over. Then you are trying to build the model. Okay, so let me explain. Tf.keras.model.sequential. What does this sequential mean? So this line means that you will be creating a model in which each layer, like you will be creating a model which has a lot of layers, right? It will be one layer, then another layer, then another layer. The shape of the model will be in layers, right? This is what sequential means. One by one, each layer will be placed. Then you have keras.layers.flatten. Flatten means we are converting a 28 into 28 input shape 28 and 28. As I told you that we had 28 and 28 size picture, we are converting that 28 and 28 shape back into 784 pixels, right? So this will transfer that 28 and 28 shape into 784 pixels into a 1D array. Why? Because in an artificial neural network, we try to make the input same for all the data, right? So we'll try to make the input same, and just remember this quote: all data is the same. So whatever be the data, it would be always somehow similar. You will be always getting an x value, giving an x value into the model, whatever be the data. It could be an image, it could be a number, it could be a time series, it could be anything, and you will get a output as a y. So here what we are basically trying to do is we are trying to write these layers as flatten input shape, that is 28 and 28, and give it a 74. Then we are having dense, which consists of 128 neurons, and the activation function ReLU. ReLU is a newer activation function. You could actually read more about this function on Google maybe. And what this actually does is it will take a input value, and then based on that input value, if it is less than a threshold value, then it will not blink, or maybe it will give you a return value of 0, and otherwise it will return a value greater than 0. We could also use other activation functions like sigmoid, tanh, but I mean, yeah, for simplicity's sake, let's use ReLU, and you can explore more about those functions on Google, and maybe try exploring stuff and reading Medium articles and blogs. And then we have dense of 10 neurons. 10 because we have 10 digits, so 0 to 9. And then the loss function. Loss function is sparse categorical cross entropy. What we are trying to do here is sparse categorical cross entropy is going to categorize the data into 0 to 9. And the thing here which we are trying to do is we are trying to categorize the data into 10 categories, not 0 or 1, not maybe 2 categories, into 10 categories, and using from log x equal to true. From log x equal to true, what does this do? This is used here because I am not using the softmax function. What is the softmax function? Softmax function is used to classify the data into the categories, but in order to show you a better intuition, I am not using the softmax function. I'll just show you how. So sparse categorical cross entropy is a loss function which we'll be using to classify the data into categories, 10 categories. Then we'll be using model.compile. Model.compile, just you can specify what kind of optimizer do you want for backpropagation. Backpropagation is nothing but updating the weights and the bias term for the model to function. Like I told you, when you are building the neural network, it will go on back and try to find the patterns, update the weights and biases. That's where we'll be using ADAM. ADAM is a bit advanced optimizer, it is better than normal optimization. It combines two techniques. It is a bit complex, but it is very universal. It combines RMS prop and it combines two techniques, RMS prop and momentum. But again, it is a simple function which helps you update the weights and biases, and then helps the model build itself. Then you equate the loss function, put the loss function here, and put the metrics here. Metrics accuracy, each step when we train, each step will display the accuracy, so we can put the metrics here. Then we do model.fit. Again, we try to fit the line. If you remember that which I told you earlier on linear regression, we'll try to fit the line in order to like fit the model on the data. And we do 5 epochs. Epochs here mean the number of times you are training on the data. So basically you train it 5 times, and then we can just do model.evaluate. You can see the loss and the accuracy over here. Then we do model and evaluate. Evaluate will check how good our model is performing on the test data. You go for x underscore test and x y test, and verbose equal to 1. So this will show us the details. This is the loss and the accuracy. Okay, 7% loss and the 97.5% accuracy. And here we have the model ready, and it is predicting. Now, if you want to go and play around with this model, and if you think that this is a bit theoretical, you can actually put your own images to test, and this is very simple. I'll just show you how. You can import computer vision library and test a random image. So you just do import CV2. It is an OpenCV library, and then you do def. So OpenCV is basically an image library. You can work with images using OpenCV. Just do import OpenCV, create a function def get image path printer equal to true, and this is just a variable. And okay, now just go to image cu2.imread cu2imread grayscale. What this will do is this will read the image as a grayscale image. What is grayscale? Grayscale is black and white. Basically, it will convert the image into black and white and then read it and store it in original image. Why black and white? Because it will then help us process the image faster comparatively compared to colored images, because it is black and white, so it has lesser number of channels. Then we print the original dimensions of the image, and we print and we do resize. You do a resizes the image into 28 pixels, because again we need to input the values in the model in the same format that we had with the MNIST dataset. So we'll just do it in the 28 size. Then we return the resized image. So you can provide the path here, and the path could be passed into the function. That function will get executed, and then you see the image being returned here, and then you can do plt.imshow to show you the resized image. So this is the image which I was using, test.3. If you want to upload the image, you can just go on this, click on this upload to session storage, and it will take you to your system, and you can select an image from that, and you can just upload it. Like I uploaded this image here. You just need to upload it. Then you just have to click on this and copy the path and paste the path here, and just run the code. You will get the image here. Resize image equal to np.expand dimensions. Again, I have to make it in the same dimensions. This was 28 and 28, right? So I have to make it into 1 into 28 and 28. This signifies that this is one dimension, this is 1, and np.expand dimension does nothing but just expands the dimension into 1 into 28 and 28. Model.predict will take in the resized image and then calculate the prediction. So this predict will actually take the image, and then it will give you a PRE. So we'll save the predictions in PRE. PRE is in a NumPy array with these values. You can see here. So these values, okay, so if you observe, this is minus, this is, if you observe the position of these values, okay, let's see the position. 0 1 2 3 4 5 6 7 8 9, right? So if you see the value of the highest value which we have here is this 4204, and what is the position? It is at 0 1 2 3, so we'll get 3. And so basically this means that the model has predicted the highest value to be at third position. I mean that starting from 0th index to the third position, so it should be the number 3. And when we write it np.argmax, it gives the highest value of the whole array as the index of the array, and that we get the number 3. So basically I tried to load the number 3, and it gave the number 3, so our model is working. You can try with different images, and you can try different combinations with this. So that is how you actually predict this number. and then we can just come back to our PPT. This actually brings us to the end of almost the end of the session. Just 1 second. You can connect with me on LinkedIn. You can connect with LinkedIn. My link, like you can just copy this link and like just search about me, and you can just connect with me, and you can maybe hit me up anytime about machine learning, and I'll be always open to communication. So yeah, you can just hit me up on LinkedIn anytime, and you can also follow ISTE-VIT Valor. These are the different handles that we have. So to keep updated with the capability with the events that we are having. So do stay updated with us. We will be having different sessions and like different webinars soon. And yeah, so basically this is now we come to the end of the session, and the attendance form will be in the chat box. Do fill it. The feedback form will be in the description. If you like the session, please like give a feedback or like give any improvements that you want to suggest. Like, share and subscribe. And again, thank you everyone for coming to the session. Stay safe, stay healthy, and keep everyone safe, because this is a hard time and we all need to stay together and strong. Thank you everyone for coming to the session. See you sometime. See you in the next video, or maybe see you soon. And thank you for joining. Stay safe.